get started, right? So it's my honor to introduce Ignacio Grossmann from RRD Dean, University of Professor of Chemical Engineering at Carnegie Mellon. And he's also the director of Center for Advanced Process Decision Making. Well, as Jorge was also mentioning, he has many honors. Most notably, he is a member of the National Academy of Engineering, and also he's received many awards from Informs as well as the American Institute of Chemical Engineers. The first Sargent Medal by the Institution of Chemical Engineers, multiple honorary doctoral degrees, and he's incredibly productive, authored over 700 papers, supervised 62 PhD students, and that's just the immediate descendants. I saw a picture, a family tree of Professor Grossmann's descendants, and I don't know, there must be hundreds of students and students of students and so on. And today, Professor Grossmann is going to talk about generalized disjunctive programs and global optimization, optimal solutions to disjunctive programs. Those in my IP class know what disjunctive programs are. And we're looking forward to your talk.
Okay. Well, thank you very much, SMJ, for a very kind introduction. And again, it's truly a pleasure, to give the seminar again. Of course, I would have loved to be at Evanston at your department, but well, that's the reality these days. In any event, so I hope that again the seminar I'll be presenting to you is one that kind of reflects one of the areas we've been working for the past few years. So let me share the screen so that we now do this. We can switch to the slides. Okay, there you are. You can see my slides, right? I hope. Can you hear? Can you hear me?
Yep. Yes.
Very good. Okay. Yeah. So again, the talk today will be aimed at the global optimization of nonlinear generalized disjunctive programs. I'll explain exactly what that means. And basically, the motivation here comes from the fact, as you might know, I have been working for a number of years in the area of mixed integer nonlinear programming. That's optimization problems in which you have both continuous and discrete variables, commonly 0-1 variables, as indicated here. And of course, you want to optimize a given objective subject to, in this case, say inequality constraints with the variables x and y. And the more common case here in terms of assumptions is to assume that these functions f and g are convex. So sometimes people refer to this as convex MINLP, although of course mixed integer is inherently non-convex because of the discrete nature of the variables. But a lot of the work has really started with the assumption of convexity. And if you're interested, there's actually recently a review paper that we wrote with my student David Bernal, and also Jan Cronquist, who's actually at Imperial College with Ruth Meisner, on reviewing and comparison of solvers for convex MI-NLP. Mixed integer nonlinear programming has actually been, a fairly active area of research. Here I'm just listing sort of the basic algorithms, branch and bound benders, outer approximations that will work, extended cutting plane. But what's been very surprising to see is the large number of different computer codes that have been generated in this area. These are still by and large academic codes. And what's also interesting to see here, if you look towards the bottom, Baron, Cohen, Skip, these are actually global optimizers for mixed integer nonlinear programming. So still, a fairly challenging area. In our case, one of the recent codes that we developed, it's called MintPy. It's Pyoma-based. I'll mention that very briefly at the end of my talk. It's again one of the codes we've been developing. That one is actually aimed at convex MINLPs. And one other interesting development is we see these days in codes like Cplex and Gorobi also starting to move a bit towards mixed integer nonlinear, at least in the context of mixed integer quadratic programming or quadratically constrained programming problems, which are in fact also non-convex. Now, today I'm not going to talk, of course, much about MINLP, but I did want to convey the idea. This is still, of course, an active area of research. I'm giving here you 3 examples that come coming from my group. One is a feasibility pump work, because an issue in MINLP is always how to generate a good initial guess. The second paper is improved quadratic cuts, where we replace the linear, mixed integer linear master problem by a mixed integer quadratic programming problem, and that's been the more aim of the second paper. And the last paper is one again with Jan Cronquist and my student David Bernal on using regularization in second order information for convex MINLP. And the main motivation or objective is to improve both the robustness and the efficiency. So there's still, a big area of research, but what I'm showing here is just one example. In the case of a quadratic, where we see, for example, we're putting here the number of instances versus relative time, and how, for example, the idea of replacing the mixed integer linear by an MIQP actually does lead to improved performance. But again, I'm not going to dwell on this aspect, but rather I'd like to concentrate on what we call generalized disjunctive programming. The idea here actually was originated from the late Professor Egon Ballas, who, as you know, was here at Carnegie Mellon. Unfortunately, he died in 2019. And he was really the inspiration for this type of work, because he's been one of the pioneers in the area of disjunctive programming. And with my student Brahman, what we did at the time was to kind of take a step further with disjunctive programming in the following sense. We wanted to consider here the case where we have both continuous variables x, but now the discrete variables we represent as Boolean variables. We have an objective function, as you can see here. Then we have the common constraints, inequalities that have to hold true regardless of the discrete decisions. And the discrete decisions are captured in two ways. One is basically through logic propositions. So we use propositional logic as a starting point for our formulation to capture the logic on the discrete space. And then the logic in the continuous space we capture through the use of disjunction. Disjunction here is basically you have an OR operator, and the OR operator has a number of disjuncts, and each disjunct, as you can see here, has associated a Boolean variable, which is acting really like an indicator variable, meaning if that variable is true, then we need to enforce the inequality constraints, and we define a cos here like a fixed cos gamma k. If y is false, we just simply ignore. So you could think of this as being also like an if then else type of construct. Now, why do we do this? Well, we're coming from chemical engineering. It's been really very important for us to be able to model a variety of different problems. And we have found that this representation, it does help a lot in the sense that you could think of it as being a high-level representation for modeling before you actually are forced, as we do like in the case of MI-NLP, to start writing constraints in algebraic form. So that's been, I would say, the major goal. The other one, as we'll see, you can actually also use this framework to derive different mixed integer nonlinear programming formulations, and also get some understanding what are the trade-offs when, in terms especially of relaxations, when you use one scheme versus another. So that's basically the motivation of this work. Now, today, I will focus on the case where the function safe in the objective, the constraints, the inequalities are non-convex. But before we go to that level, let me just show you first a simple example problem to give you motivation for this kind of work. We have here number of streams, pools, and products. And basically what we want to determine here is, of course, what is the optimal structure of or subsystem from that superstructure in terms of what streams we should select, what pool, and that then give rise to the specifications of the products. And you can see here, if you use the formalism of generalized disjunctive programming, we basically write down the equations and mass balances, but we have disjunctions and the selections of the streams, whether you select it or not. If you select, then you incur an fixed cost. Otherwise, you set the variables to 0. But the other one here is in terms of the selection of each pool. So here, basically, if you select, then again, you apply blending equation. And here, the complication arises from the fact that we have bilinear equations, which then introduce non-convexity. If, on the other hand, you do not select the given pool, you just simply trivially set the variables to 0. So this is the way we would formulate the problem. In this case, you can see it's fairly small scale problem. There's 24 bilinear variables, 9 discrete variables, and this is the optimal structure that we obtain with the type of algorithms that I'll be describing here. Now, so basically, how do we, in general, approach these problems with disjunctive programming? So as we'll see, this is just to give you the general overview. One is the philosophy of taking it as a starting point to reformulate the GDP into an algebraic mixed integer nonlinear programming. And here we'll see the two extreme reformulations are the big M, which is sort of the traditional one used in integer programming, or we can also use the Hall relaxation, where we intersect the convex hull of each disjunction. And here we can apply any of the major algorithms that I briefly alluded to. The other way of approaching the problem is through what I would call logic-based methods. So here, one approach could be a logic-based branch and bound. So you actually branch on the disjunctions rather than converting the problem into a mixed integer form. Or the other one is actually also to use some decomposition. Decomposition, as we'll see at the end of the talk, is very important because it allows us to reduce the complexity of the nonlinear programming subproblem. So that's kind of to give you the general view of how we will actually approach these problems. But here we need to start first with the case where we do assume that the functions are convex, because that's going to be basically then the basis on which we can then build on addressing non-convex optimization problems. So here again, we assume that the functions f, the constraints r, and the inequalities g are actually convex functions, and using the same formalism as we saw before. Now, an interesting question that arises here when you have a problem in this form and say you want to convert it into some algebraic mixed integer form is to ask the question, what is a relaxation? Because we know relaxation is, of course, very important in terms of providing us a lower bound. And here, of course, at first sight, if you have Boolean variables, it's not obvious, of course, how you actually develop such a relaxation. But the way you actually do this is, for example, if you use the big M reformulation, what we simply do here is, first of all, each of the Boolean variables gets replaced here by 0, 1 variable lambda. Okay, so that's the first thing that we do. The logic constraints gamma y equal true, we can replace by a set of linear inequalities. This comes from the work of Paul Williams, London School of Economics. And then what we do with the disjunctions, we just simply, each term for the inequalities, we introduce the big M multiplied by 1 minus lambda. So if lambda is equal to 1, we enforce the inequality. If lambda is 0, then this constraint becomes redundant. And basically for each disjunction k, we enforce that exactly one of the terms be hold true. So in other words, exactly one term of the disjunction needs to hold true. And this is, again, the standard sort of big M formulation that you also see in the sort of basic text on integer programming. And again, here then we have the mixed integer reformulation of the GDP is one of the ways that we can address that problem. When we do the relaxation, of course, we just simply treat the lambdas as being continuous variables between 0 and 1, and that then gives us a lower bound to the solution to the problem. But what's interesting about the formulation of the GDP is we can think of other reformulations, and in particular, we're introducing here what we call the Hall relaxation. The idea here is the following. So we consider each disjunction, take the case of the kth disjunction here, and what we want to do here is determine the convex hull. Now, it turns out the convex hull, this actually comes again, extension, I have it here at the bottom. On the one hand, work from Egon Ballas that was addressing linear problems, and actually also work by Professor Marotra in your department when he looked at 0, 1 mixed integer problems. The idea here is that for a given disjunction, you can actually write down, if you wish, algebraically, the convex hull. The way you obtain the convex hull is you disaggregate the variables x into these variables nu. So it's like a, higher dimensional representation. And then here we introduce the upper bound constraint so that if lambda is equal to 0, you force the disaggregated variable to be 0. And of course, only one of them can be non-zero. That's why we have the constraint summation lambda equal 1. Although in this case, I'm showing this in continuous form. And here, the part that is maybe not so obvious is this inequality constraint, where basically each inequality we multiply by lambda, and the argument is nu divided by lambda. And this function, I'll explain that in a moment, but basically this then gives us the convex hull of the given disjunction. And if we intersect the different convex hulls, then we obtain the hull relaxation, which is of course not equivalent to the convex hull of the oral problem, but at least we're intersecting convex hulls. And the issue here is precisely this function, the lambda g nu divided by lambda. This is called the perspective function. So this is the representation that is used to derive the convex hull for a set of convex inequalities. Now, so the issue then here is what we can do then. If we go back to our problem, let me just remind you here, with the cost function, because the gammas here is going to be constant, we just simply take that as a linear combination. So when we do the reformulation, the cost part of the function is here. And then what we do here, instead of using the big M constraints that you saw before, we replace for each disjunction K the equations that constraints that define basically the convex hull. And here, of course, again, you get the perspective function. I'll talk about this briefly. And here we're assuming first that the lambdas are continuous between 0 and 1. And obviously this is a nonlinear programming problem, a convex nonlinear programming problem, because as we'll see in a moment, the perspective function is still convex if the function is convex. And that then gives us a way to compute in a different way a lower bound to our generalized disjunctive programming. This is in contrast to the big M. Of course, there are trade-offs. The trade-off here is because we have a higher dimensional representation, we introduce more variables, we introduce more constraints, but then the good thing, we're going to get a tighter lower bound. So that's basically if you wish a trade-off versus a big M. And here, if you want to solve this directly as an MNLP, all you need to do is to simply specify the lambdas to be as 0, 1 variables, because remember, the logic constraints we represented through linear inequalities, because we're starting from propositional logic. Now, so here then, the question is, how do we relate the two, the big M and the hull reformulation? Well, as you can expect, this can be proved fairly easily, that the relaxation of the hull relaxation gives us a lower bound that is greater or equal than the lower bound from the big M formulation. In a simple algebraic representation, geometric interpretation of this result is shown here. You can see you have two variables, x1 and x2. If you project the equations of the convex hull into the space of x1 and x2, you get exactly the convex hull. So this is the tightest feasible region that contains, it would be a disjunction where we have the three circles, means so you are either in this constraint, in that constraint, or in that constraint circle. So being within this region gives you then the tightest representation. On the other hand, typically what the big M formulation will do will actually overestimate, obviously, the convex hull, and that gives you sort of just a qualitative explanation on why the hull relaxation, or at least when you do the convex hull, you get a tighter representation. Remember, hull relaxation means we're intersecting convex hull of each disjunction, okay? And that's, of course, not equivalent to the convex hull of the original problem. Now here, a major question that arises is, how do you deal with a perspective function? Because remember, perspective function, as we've seen in the previous slide, is lambda, the variable lambda, multiplies g nu divided by lambda. Now, the interesting thing about the perspective function is that if the function g is bounded in convex function, then the function h of the perspective is also bounded in convex. Okay, and that comes from nice work of Routhier and Majoral. And also, we can have the condition that for lambda equals 0, h is equal to 0. But the question is, how do you actually implement the, so if you remember when I presented to you the master problem here, this is the, if I do the relaxation, I have to solve this nonlinear programming problem. How do we actually solve for the perspective function? How do we handle that in our formulation? Because we cannot simply divide lambda by 0. That's going to lead to singularities. So one of the approaches that we have taken here is to replace a perspective function by this approximation. This approximation at first sight looks rather complex. The only thing that we're doing, lambda here is being replaced by 1 minus epsilon lambda plus epsilon. Okay, 1 minus epsilon lambda plus epsilon. Same thing here when we divide by lambda, it's 1 minus epsilon lambda plus epsilon. And then we subtract here minus epsilon g at 0, 1 minus lambda. Of course, at first sight, this looks a little ugly. It doesn't look, very nice, but we have some nice properties, as we'll see in a moment. The first obvious one is that if epsilon goes to 0, then of course we get an exact approximation in the limit, but well, that's more or less the obvious result. But from a numerical point of view, what is interesting here is that the constraint that I'm showing you here is exact at lambda equals 0 and lambda equals 1, regardless of the value of epsilon. And this is shown here. If lambda is equal to 0, okay, you end up here with this term epsilon g of 0 that you have here. With lambda equals 0, this reduces again to epsilon g of 0. This cancels out. So we have the exact representation at the value of lambda equals 0. And we also have the exact value when lambda is equal to 1, because when lambda is equal to 1, the epsilons cancel out. You get here a coefficient of 1. Then this is g nu divided by 1. And then the term here with the 1 minus lambda is again vanishes, so we get the exact representation. So this is one of the ways that we have been using in the recent past in order to address the issue on how do we handle the perspective function within this formulation. The other important thing here that should be noted is that if the function g is convex, then this approximation function is also convex. So we maintain that nice property. And again, I should mention what was interesting about this approximation. It came out actually at a meeting with Kevin Furman from ExxonMobil, was attending a meeting. My student Ignacio was giving the presentation. It was the discussion that we basically ended up with this type of representation. On the other hand, of course, it would be nice if we had something more exact. And here, just very briefly, I'm not going to go in details. Recently, what we've been able to also establish is that if you, rely on conic programming, in other words, you represent the constraints are represented through cones, that you can actually obtain an exact representation of the perspective function. So you don't need to rely on the approximation. But the trade-off here is, of course, in order to get conic functions, you need to have specified forms of the functions. These tend to be typically polynomials or exponentials and so forth. So it's not immediately obvious how you apply them, but the important thing, if you can exploit that structure, then you do not need to rely on the approximation. Okay, so let me just give you an example to see how these type of formulations work. This is a simple network problem. We have the possible choice of these 8 different blocks. These are represented as different processes, and we have conditions here. You pick either 1 or 2, an exclusive OR, 4, 5, 6, and 7. And so this problem can be formulated explicitly as a GDP problem. This is the optimal solution. So you can see, you select here, for example, unit 2, 4, and 6. Some of the other units vanish from what we call the superstructure. And this is the optimal solution. Now, it turns out that if we write the GDP and you convert it into a mixed integer nonlinear programming problem, and if you apply a branch and bound method, so in other words, we do a tree enumeration where we solve a nonlinear programming relaxation at each node, you can see here that the initial lower bound is 62. The optimal solution is 68. So in this case, it actually takes a total of 5 nodes to find the solution. That is, if we use the branch and bound and use the representation with the whole relaxation. So in other words, we apply convex hull to each disjunction. On the other hand, what happens if we use the simpler big M? If you use the big M, well, you can see here, first of all, you get a much weaker bound. The lower bound is 15 versus 62.8. And then, of course, that also means that you now enumerate a larger number of nodes in the tree. So in the case of whole relaxation, we'll enumerate 5. Now, in this case, with the big M, we enumerate 17. Granted, the one thing, to be fair, of course, in the big M, we're solving smaller NLPs at each node. So it's not immediately always true that that's going to be that the whole reformulation will always be more effective, because it could be that the cost of the extra variables and constraints could make the computational cost to be larger. But in this particular case, of course, turned out to be the whole reformulation that actually worked. It was also faster, not only in terms of nodes. Okay, so that's a simple example. But now an interesting question that then came up in our work was to say, well, we have two ways of finding the lower bound, the big M and the whole reformulation. And the question is, can we do better than that? Is there any way to obtain stronger relaxations with the whole relaxation? And here, basically, our work was inspired, but I really have to give him enormous credit. Professor Egon Ballas, he was truly a giant in the field of integer and disjunctive programming. He, by the way, still managed to write a book that appeared in 2018. It's a book on disjunctive programming. And actually, what was interesting, that book he actually used to teach a short course in our department in chemical engineering, because Egon always, had kind of a very nice relationship with us in chemical engineering. So he actually taught the half of the semester in our department this course. It was, as you can imagine, really unforgettable experience. But now the question then here is, what can we do with what Egon had developed? He concentrated, first of all, disjunctive programming means it's like linear programming with disjunctions. There's no Boolean variables, there's no discrete variables. That's the first thing. So it concentrates on, polyhedra. And what we wanted to do is to see, can we extend some of that knowledge, some of that nice work that Egon had developed to nonlinear complex sets. And basically here, this was now the interesting sort of observation. Can we convert the GDP, the generalized disjunctive programming problem that has the continuous and the Boolean variables, to a nonlinear disjunctive program that has only continuous variables? And I remember this was actually the subject of a number of meetings we had with Egon on trying to think, well, how can we do this? And here I have to give credit to my student Sawaya, who came with this very nice idea to say, well, it turns out, how about if we do the following? Instead of writing here the Boolean variable, let's introduce the variables lambda that we had before. So again, the logic constraints get represented by the linear inequalities that we have here. But then now here, in this case, what we do for each term of the indicator variable becomes now if lambda is equal to 1. We have the condition that summation of lambda is equal to 1. And what is interesting here is we can deal with the lambda as a continuous variable. So this is a problem all with continuous variables and with the disjunction. And the beauty here is that the integrality of lambda is guaranteed because of the fact that we have precisely this disjunction, because only one lambda can be true. Okay, so this established a nice connection between GDP, which was sort of the approach we had developed, and disjunctive programming, which was basically, the approach that, Professor Egon Ballas had been working on. And basically then here, we can establish the proposition that the discrete continuous GDP and the continuous disjunctive programming are equivalent and yield the same solution. Now, why was this significant? Because now we could make a connection with a wealth of, theory that Egon Ballas had developed for disjunctive programming. And basically here, the first concept is the one of, quote, equivalent convex disjunctive programs. So here the idea is, first of all, what is called a regular form. Regular form is intersection of the union of convex sets. The way to think about this is simply, like in the formulation that I presented, you're really intersecting the set S, and the set S, which is a disjunction, is really the union, in this case, of convex sets. It was a union of polyhedra, in the case, of course, of the work of Egon Ballas. So regular form is just simply, again, the intersection, okay, of disjunctions, and the disjunctions are basically the union of these convex sets. And here, the interesting result, and this is what motivated our work, was to say, well, it turns out there's this very nice, interesting theorem by Egon Ballas, which was published in 1985, which establishes that if we're given this initial regular form, which would happen to be the one that we have in our GDP problem, then F can be brought into disjunctive normal form if we perform cardinality k minus 1 basic steps. Okay, now what is a basic step? A basic step is basically you intersect successive disjunctions, okay? And if you do this k-1 times, then basically you obtain what is called the disjunctive normal form. Now, why is the disjunctive normal form interesting? Because if we get the disjunctive normal form representation, then we can actually generate the true convex hull of our problem. That's basically the significance basically of this theorem. Now, I realize this is not immediately so obvious to understand, so let me give you an example to illustrate what the meaning is of these so-called basic steps. So let's say I have this regular form F. I have three disjunctions. I'd say S1 intersects S2 and S2 intersects S3. So it's three different disjunctions. Each disjunction is really the union, right, of these sets, P11 or union P21 and so forth for S2 and S3. So basically what that theorem is telling us is that if you have that representation, you can bring it to the form of the disjunctive normal form if you perform two basic steps, because we have 3 minus 1, it's 2. So remember, cardinality k minus 1. So it's two basic steps. So the first basic step we're going to do, we intersect S1 and S2, the first two sets. When you intersect them, basically what it means, you're going to distribute the union over the intersection. And that then means that you get a total of 4 terms because you distribute P11, intersection P12, and so forth. You get now, it's basically all possible combinations of the intersections that you can have, and you take the union of them. That is called a so-called basic step. Now, so this is the first one. So now what we're going to do, we're going to rewrite this and say, well, what we have obtained here, which is S12, I'm going to intersect now with the third set is 3. And if we perform that operation, basically, this is what we need to write down here. And here, basically, we obtain a total of 8 different terms. So it's basically all the possible combinations of the intersections of the various sets. And that's basically what then takes us to what is called the disjunctive normal form. So it's just simply the way to think about it. It's all combinations of intersecting these sets. And why is the disjunctive normal form interesting or important? Because now we can establish this interesting theorem. This came out from the work of my PhD student, Juan Ruiz, who's actually University of Texas in Austin. And the theorem is basically the following. It states that if you have a disjunctive programming problem, okay, with convex disjunctions, and you bring them into the DNF form, meaning that we would have to perform, all the basic steps that I outlined before, the cardinality k minus 1, okay? And if the function, again, is bounded, then the GDP problem, the generalized disjunctive program, is equivalent to this nonlinear programming problem. That's the significance. So we can think of converting our discrete continuous, discrete logic, if you wish, GDP problem into a nonlinear programming, which is a continuous problem. So at least theoretically, that's obviously a very nice result. And here again comes, if you look at the formulation, it includes, of course, perspective function for the constraints and also the objective, which gets transferred here into the constraint. And the result that I have here has actually two interesting parallels. One is in the case of mixed integer linear programming. You may have heard about the theory of convexification, Lovász-Stryver, Shirali-Adams, and the work of Balaseria and Korn-Jules. There are different ways that you can actually convexify an MILP, a 0-1 MILP, I should clarify, into a linear programming problem. So this is the counterpart of that. And the result I'm presenting here is actually also related to some nice previous work, one by Suarez and Seria at Columbia, and then here at Northwestern, Professor Marotran. In the case of Sarah was applied to pure disjunctive programming, no discrete variables. In the case of Professor Marotran, his students stops for 0-1 MINLP. Okay, so that's the sort of the nice theoretical result that we can theoretically convert the GDP into a nonlinear programming problem. Now, what's the problem? The problem is, of course, if we apply all the basic steps, it's an exponential number of them. So instead, what we're going to do is to use this concept of hierarchy of relaxations. The idea here is simply the following. So let's assume we consider now a sequence of these regular forms where the form Fi is obtained by applying a basic step to a previous regular form. So in other words, what it means is you have the whole relaxation of Fi minus 1. I apply only one basic step, and that new basic step is in the set Fi. And then what this theorem establishes is that you can show that the projected feasible region of that problem is contained in the feasible region of F1. And here again, it's maybe easier to see this with a simple geometric example. So I have here two disjunctions. One disjunction is either you're in the big circle on the low or big circle on the upper part. The other disjunction, you're the little circle on the left or the little circle on the right. These are the four disjunctions that we have here. Now, if you apply the whole relaxation, what it means is you take the convex hull of the two big circles, then you take the convex hull of the two little circles, and when you intersect them, this is basically the feasible space of the whole relaxation of that representation. So the dashes here in red represent the feasible region of that, of the whole relaxation that is implied here. Now, what happens if you apply a basic step? A basic step here would mean that now, again, remember, we distribute the unions over the intersections. So we have now 4 different terms. And if you do these 4 terms, it turns out that the feasible region is reduced to these 2 areas in blue, the dash in blue, the one on the left, the one on the right, okay? And then, of course, if you take now the convex hull of that, it's very clear that we now have a tighter relaxation. Why? Because the feasible region of the basic, the one with the basic step, is contained in the feasible region, in this case, of the whole relaxation. Okay, so just simply applying one basic step might be one direction in which we can tighten the formulation without going necessarily all the way to the disjunctive normal form. Now, the question then here is, of course, how many basic steps do you take? So here, what we did, we said, well, let's develop some guidelines. These could be, for example, to do a basic step, there should be at least one variable in common. The more variables in common, the better. Okay, and then also if you have spaces, that can also help. That will not necessarily, if you wish, tighten the relaxation. So those cases you can identify where it's not very promising. But one that actually proved to be very useful is intersecting improper disjunctions, which means like a constraint, and introducing them into a disjunctions, an improper disjunction into a proper disjunction. So these are just, if you wish, some basic rules that we applied. And the main thing here is once you apply those rules, you end up now with a mixed integer nonlinear programming formulation, where again we have the added variables like an extended formulation. Okay, but what is interesting here, and again this again borrows also work of Egon Ballas, you don't need to introduce new 0, 1 variables when you do these basic steps. Okay, so you can basically just get the extended formulation. So here you have set of disjunctions before the basic steps, and here the set of disjunctions after the basic steps. Again, I'm not going to go here in detail, but just simply to convey the idea that once you perform a basic step, then of course you increase the size of your MINLP problem, but the number of 0, 1 variables remains the same. What changes is the number of variables and constraints. Okay, now, so let's go back to our little example. Remember, this is the example I presented where we applied big M and we applied whole reformulation. So in this little problem, what we did here was actually to simply apply the improper disjunctions equations and introducing them into the disjunction. So basically what happened here, we then doing the basic steps in that form, which led, to a relatively modest increase in terms of the problem size. We found that we could obtain the optimal solution at the root node. So basically, from the whole relaxation with the basic steps, we obtain the solution without the need of performing any branch and bound. So this clearly shows, if you wish, the potential use, of the hierarchy of relaxations that can help us to tighten relaxation. This is, of course, this is not meant to be, this will always happen, but it just simply comes to show how before we needed 5 if we did whole relaxation, 17 notes if we did the big M. Now, in this case, if we did the whole relaxation plus these special basic steps, we could solve the problem as a continuous nonlinear programming problem. Now, here, we apply this to a number of test problems. We compared the big M, that's here, the whole reformulation, the two we had seen before. And the proposed approach here is when we applied some of these basic steps using some of these rules, okay? And basically what happens, I'm just pointing out here, the last 2 problems, just to make the point how the problem size increases. The number of continuous variables, number of constraints, you can see more or less doubles when you go to the whole relaxation. And now when you do the basic steps, it increases even more. For example, the lower one, we had here 53 continuous variables. We go here now 641. So the problem size greatly increases. So that's, if you wish, the basic trade-off that we're going to find, but we'll see a bit later. There is a way to get around through that through the use of cutting planes. But basically, the idea then here is to see what is the effect of applying directly such an approach. Well, here we're showing the main message here. I know there's a lot of numbers here, but the question, the big M, is the one that gives by far the lowest lower bounds here. For example, this is 0, this is 115, 117, 0 big M, 0 whole relaxation, 224 with the proposed approach. But more than that, we can see the whole relaxation improves on average 50% the bounds of the big M. And then what is very striking here, the process type of problem I presented before, you can see big M gives very poor lower bounds. You get much better bounds with the whole relaxation, minus 829, 67. And then furthermore, what in the case of the proposed approach, we could obtain in all cases stronger, of course, stronger lower bounds. And here actually, in those 2 examples, if you look at the number of nodes that were required was 0. We found the solution. This was actually the example that I presented before. But basically, the bottom line here from these examples is that the proposed approach of applying some of the basic steps was faster in 10 out of the 12 problems versus the big M, and versus whole relaxation in 8 out of 12. So it's not uniform because, again, we're paying the price for the increased size of the whole relaxation. Okay, so that's basically what we have done in terms of convex problems. The question now is what happens if we would like to address non-convex problems? In chemical engineering, it's very common that these functions, a lot of functions tend to be non-convex, so we have to contend with that issue. There are some problems that, yes, can be formulated from the outset as convex optimization problems, but it's not often the case. So the approach that we took here was the fun to say, well, how about if we do the following? If we somehow use this theory that we have developed to strengthen lower bounds, but for the global optimum. In global optimization, one of the things that is extremely important is the quality of the lower bounds. Okay, if you get good quality of lower bounds, you have much. Global optimization problems are, of course, NP hard. They tend to be usually very difficult, very expensive to solve. So what we did here was to say, well, take your non-convex GDP, the one I presented before. What we're going to do, we convert it into a convex GDP in the sense that we replace the convex functions by under and overestimating functions that are basically convex envelopes. Classical example, bilinear would be the McCormick envelopes, for example, or in the case of concave, the secant, and so forth. Okay, there's a number of functions that we can use here to convert our non-convex GDP with a structure to a GDP problem. Now, we could leave it there and say, well, that's the lower bound that we're going to obtain for the global optimization. But the idea here was to say, well, how about if we actually tighten, if you wish, the GDP problem precisely by applying these basic steps. In that way, we'll be able to obtain stronger lower bounds for the global optimization. Okay. Now here again, the remark going all the way to DNF is not practical, so that's why we rely again on just some basic rules to do some of these steps. And also for global optimization, what is important, we can also infer tighter bounds on the variables because the convex envelopes are highly dependent on the bounds on the variables. But that's a secondary point. Here I have just a little example that shows you kind of the basic idea that we're trying to apply here to see the effect of the basic steps for the purpose of global optimization. Simple problem. I have from material A, I have two possible choices of reactors to produce B. So problem here in the form of GDP, the variables are F, flow, X is conversion. So the problem here is we want to maximize, in this case, the profit. Okay, so objective function is the negative, we minimize the negative of the profit, okay? Then we have here the disjunction for the selection of the reactor. If you select reactor 1, you have some linear equation that relates to flow and conversion. If you select the other one, you have a different linear correlation for that. And of course, only one of them can actually be selected. And then of course, we also have a constraint for the demand. The flow times the conversion should not exceed the amount D that we require of that product. This is a very simple, nice problem because we can plot it. You can see here, you get F on the y-axis, you get X that lies between 0 and 1, F in this case is between 0 and 8. And it turns out this constraint here, the demand constraint, actually is the one that produces this region to be actually non-convex. Okay, it's a non-convex constraint, it's bilinear. What's also interesting, if you now plot the feasible space for the reactors, you're going to find out that actually reactor 2 is totally in the infeasible region, so it's not feasible. And reactor 1, okay, is feasible, but you can see it's only feasible in this portion and feasible in that. So it's actually discontinuous. So what's remarkable is that this very simple problem has, you know, already this kind of complexity. So we'll see geometrically what is going to happen here. So what we're going to do here, this is the optimum solution, by the way, it's -1, 0, 1. Okay, so let's see with what we know, how could we can help to find this global optimum, okay, which is again not even this simple example, not that trivial to find. So what we're going to do then here, we take our problem, and then what we're going to do here, the terms fx, which are bilinear, were replaced by the inequalities, the McCormick inequalities for the convex envelopes. And as soon as you do that, then you can see here what happened is that the curved part of the region gets replaced by these linear constraints, and we now have a convex region, okay, with basically a polytope here, given those constraints. And then next, what we are going to do then here, we then take the convex hull relaxation of the two disjunctions. So that means it's basically the reactor 1, reactor 2. And when you intersect them in the region, it's the region in red. That's a feasible region that the optimization will look at to find the best solution. That's going to be obviously a lower bound. And if you solve that problem, the lower bound that you get here is -1.28. Okay, so this is just simply applying the whole relaxation. And we're going to see here what happens if we now do a basic step. Now, what does that mean? It means that now, okay, I take the bilinear terms as we had before. We replace them with the convex envelopes, the McCormick, but now a basic step is intersecting. This is an improper disjunction, the convex envelopes with a proper disjunction. We introduce them in the disjunction. This is as simple as that. So that's now the basic step. And now what is interesting, when you plot the feasible region and you do the convex hull for this basic step that we perform, this is the line in red. So clearly now we have a restricted, a smaller feasible space by performing this basic step. And what it means is basically now we get a lower bound, which is -1.1, which is actually stronger than the one that we had before. So again, it's a very simple geometric example just to give a little bit of a feel. And again, we've applied this to, for example, these are small problems, but were representative just to get some, like these were bilinear and concave functions, okay, again, small size, all those linear fractional, polynomial, and exponential. And here, basically, what we're showing is comparing, this is the global optimum in these different problems that we have. Okay, it's a total of 10 problems. And this is a lower bound that you get if you only apply the whole relaxation. So you don't do any basic step. And you can see, by and large, in some cases, it's not too bad. But in some cases, like the pool problem, this is much lower than the global optimum. Now, what happens if you apply the basic steps? It turns out if you apply the basic step, you obtain, of course, significantly stronger lower bounds, like for example here. And well, two things. What I'm showing here, this is the lower bound after performing some of these basic steps, following some of the rules that I just outlined very briefly. As an example, if you look at the last problem, you can see the lower bound with whole relaxation is 38,000. With the basic steps, it's 48,230. It's very, very close to the actual optimum solution. But what's also very interesting here, this is the lower bound if we went all the way to the DNF. And what this is showing us is that without going all the way to the DNF, we're getting in 8 out of the 10 cases, basically the same solution. Okay, so basically we still get the same best lower bound. I'm not saying this is provable, but it just simply comes to show that by just applying a few basic steps that are kind of critical, we can significantly improve the relaxation. That's kind of the main message here. Now, of course, to do global optimization, we need to do, spatial branch and bound search. We typically do also bound contraction, and typically we first do the branching on the Boolean variables. And here, once we find a feasible discrete value, then we switch to a spatial branch and bound where we search on the continuous variables. So again, here, just a summary in some of the initial results give you, if you do the whole relaxation, number of nodes and the times that were required. And you can see when we do the basic steps, we can reduce nodes like from 5 to 1, 450 to 227. In this case, it remained the same. And in all cases, there was basically, some reduction also in terms of the computational time. So main point here is that we can then, using the basic steps, improve significantly the quality of the bound. But what's the problem? The problem is still the issue here that the problem size increases still quite a bit when we do the basic steps. You can see 87 to 206 and so forth. So the question then here was, what can we do, okay, in order to avoid generating explicitly the whole relaxation with the basic steps? And this is the idea that leads to what we call a logic-based approximation combined with the use of coding planes. Motivation here is that we want to avoid the solution of a large-scale NLP that would be required, for example, in what I presented before, because it's in the full space. But still, we want to get tight upper and lower bounds. So what we have here, this is sort of the representation of the non-convex GDP. This is just sort of illustrating, for example, that we have a region that may be non-convex. We have disjunctions, and these would be regions, many of which could be non-convex. So that's kind of the nature of the problem that we want to address here. So what we do is we can construct a linear relaxation. How? Basically by using these polyhedral relaxations like the McCormick, like the underestimators. And geometrically, this is what we're doing then. It's basically replacing the nonlinear, non-convex region by a set of linear constraints. In this case, these are polytopes that then give you a way of predicting a lower bound, because this can now then be translated into a mixed integer linear problem. Now, how? Well, we could do big M, we could do whole relaxation, but it's a way of predicting a lower bound. Now, but then the important thing here, what we're going to do then here, as you'll see in a second, we're going to be able to generate cuts to avoid, solving the problem in full dimensional space. The other important element here is that for the NLP, what we're going to do when we fix the Boolean variables, we're only going to retain the constraints that are true. Constraints that are false, we just remove them. That means that this NLP is actually a reduced NLP, and if it's a feasible solution, it will give you a upper bound. Okay, that's basically the idea. So you can see here, geometrically, we throw out all the terms that do not apply for the disjunctive, so we pick only one of them. And the idea then here is to solve a smaller dimensional NLP that is non-convex, that we're going to solve to global optimality. That's basically the idea. So the algorithm generically is like this. We solve the MLP that gives us a lower bound, and again, that will require we can use the example McCormick envelopes or some of the other ways of coming up with these constraints. Solving the MLP, we then fix the Boolean variables. We throw away everything that doesn't apply, and then the NLP subproblem that we solve to global optimality. Now, of course, if we get a feasible solution, that gives you an upper bound, and then you compare the bounds. If they're roughly the same, you stop within a tolerance. If not, then you go back to your MLP. You introduce an integer cut to eliminate the solution of that combination of the Boolean or equivalent integer variables. That's basically the idea of the algorithm that we have developed here. And the interesting thing here is that, of course, the issue is, can we do something about helping that MLP to give us, better lower bounds? Okay, that's basically the idea. And here I'm just, since I'm also running out of time, but I only have a couple more slides and then I'm done. So what we're going to do then here is basically the idea of obtaining a cut using the tightest possible convex envelope. So geometrically, let's assume you have this inequality Rx less or equal than 0, and it's defined by this non-convex region. And let's assume that the polytope I'm showing here is, a simple way of overestimating the function, so that you actually end up overestimating that feasible region. Now, what we're going to do is would like to generate a cut that approximates the convex solve of that function. So what we're going to do then here is the following. We're going to intersect that function Rx with itself. The formulation is here. So you define Rk for x1, that's one variable. Rk for x2, it's another variable, but these are basically the same functions. And we take a linear combination to obtain the values of x. This representation then actually gives you the convex set that contains a non-convex feasible region. Of course, generating that explicitly would be, very expensive to do. In this case, we just simply determine from the solution that you obtained from the MLP, which is this value of xj, we want to find the closest to the boundary. Okay, that's basically, and once we obtain that solution, we then generate a cut. So that cut is then sort of equivalent to having performed, if we wish, a partial basic step that can then help to strengthen the lower bound. And that's basically what we're doing here. And now what we've done then here, basically, we've added these cutting planes to the polyhedral approximation that we have of the non-convex sets. And that's in a way to improve the lower bounds. And just to finish, again, if we solve here 40 instances of GDPs, so you can see 100 Boolean variables, 700 constraints. If we applied directly Barron to the big M reformulation, you can see this are relative bounds. This is relative upper bound, relative lower bound. After 7,000 seconds, we cannot even close the gap. Now, in the case where we apply the algorithm, but without the cuts, just simply using the polyhedral approximation, you can see now we get a substantial improvement of the lower bound. Okay, so in that sense, that's a good thing. But then we still get, so you get here I'm sorry, this is the upper bound. The lower bound is the one in red. Okay, so let me go back here before I confuse you. So this is what we have with Barron. This is what we get now with the MILP. And then lastly, when we apply, oops, I'm sorry, this is now, yeah. And, oops, sorry, I'm a little too fast, sorry. Apologies for that, yeah. So when we apply the cuts, now you can see we get this curve in blue. So we can get now a much tighter difference between the upper and the lower bounds. Okay, that's basically the idea. And that's, of course, what you would expect also from the theory. Now here, we applied this actually to a multi-period blending problem with type of problem I introduced at the very beginning of the talk, where we remember we had some of these disjunctions and whether you select or not, for example, given supply tank, and the nonlinearities come from the bilinearities. In this case, basically, the algorithm was pretty much similar to the previous I presented before. In the master problem, we introduced these cuts, but now the subproblems, we have a subset of also binary variables. So the subproblem is actually in MI NLP, not in NLP. But the thing that was very encouraging for that particular application, here we're plotting the relative bounds versus the computing time. If you use skip is also a global optimization solver for MI-NLP. You can see you get this big gap. With our proposed algorithm, we could close the gap for all practical purposes after something like 1,200 seconds of CPU time. Okay, so again, I realized I went a little too fast. I just wanted to also to finish the talk by telling you that I presented, it's not all pie in the sky. There is now a system called Pyoma GDP. It has been implemented. It's actually part of a project we have with a National Energy Technology Lab. It's called the IDEAS project. And the idea here is that users can specify the problem with the GDP, and you have flexibility. You can choose to convert it into an MI NLP with big M, whole relaxation, making use of the coding planes, or you can go and directly solve it as a GDP with the algorithm I presented, the logic-based outer approximation, and the disjunctive bound that we have here. Okay, so with this, again, I apologize, I'm just reached the time limit. Just want to conclude by finishing to say that, we've shown the extension of nonlinear convex sets for hierarchy of relaxation, the important concept of basic steps. Then the one that the tightest of these relaxation, that there's a way of converting into GDP into a convex nonlinear programming, which is a nice theoretical result, that the framework can be applied also to non-convex problems. So we're leveraging the convex solution for solving non-convex optimization problems. And that basically, the logic-based approximation, which is what I saw discussed at the very last time, gives us also a way of obtaining tight bounds. Okay, so with this, I'd like to thank very much your attention. I apologize for the fact that as I expected, when they ran a little over time, but I'd be happy to answer any questions you have. Thank you very much. Thank you.
Thank you very much. This was a very interesting talk. So we started a little late also, but I understand if people have to go, we are right on time. But if you have some time, we could answer maybe a quick question.
Yeah, I think let's see. I have from Andreas. Has to run to the office, and let me see.
Yeah, but you'll meet him in the afternoon.
Yeah.
Yes,
right.
I do have a few questions, but I'll save it for my meeting.
Right. Any
questions?
Well,
maybe I'll ask one. So
sure.
For the ones that you happen to have the optimal solution, the relaxation is happens to be integer. Was there a structure to the constraints, like a special structure?
You mean in the example that no, not really. You see what happens, and that's the kind of challenging thing, is that again the structure of these. Well, obviously some of the problems like the process network, the basic structure is just simply input-output relationships, and the relaxation of those when you relax equalities into inequalities, they're turning out to be convex constraints. But usually one thing that it tends to be challenging in those cases is the fixed cost term in the objective that, cause them to, have some finite relaxation. But in that particular example, it was just simply, you see, one thing that we observed, maybe that's the generalization, it's not so much the structure of the problem, but the fact that if you go through the work of applying at least a few basic steps, as I showed in one of the slides, you can actually approach the true disjunctive normal form, which is the tightest convex whole, and then you obtain, of course, a solution as a relaxation. But again, this is empirical. This is not nothing. Sure. The theory would be to say you have to go all the way to DNF form, right? I mean,
Yeah, I mean, there's concepts of a rank of the sequential convexification for certain structured problems. Maybe applying it a couple times is enough, but
Yeah.
you will need to use the structure.
Right.
All right. Any other questions? Well, thank you very much again, and you'll take a short break and then have meetings in the afternoon.
Okay, thank you very much.
Thank you
I
for
really
the great
appreciate
talk.
your patience over that, as usual.
Oh, no, this was
I ran a little bit over time, but well,
exactly
I look forward to my meetings shortly. Okay, thank you.
All right, thank you very much.
Thank you then. Bye-bye. Bye.
Bye.
Okay, all right.